Hi everyone, welcome to the Applied in Education seminar, joint initiative between the Department of Statistical Sciences at the University of Toronto and the Canadian Statistical Sciences Institute of Ontario. Every week we bring sort of world experts in statistics, and this week we're joined by Dr. Peter Parker. When it gets to organizations that have had biggest influences on the 20th century, 21st century, it does not get any bigger than obviously NASA. And Dr. Parker has been working at NASA since 1997. Currently serves as a team lead for advanced measurement systems. He holds a PhD in statistics from Virginia Tech, as well as a master's. But in addition to that, he also has engineering degrees and is a licensed professional engineer. So bringing both sides of the picture together is sort of part of the unique experiences that we'll hopefully hear about today. And yeah, so we typically run for an hour. If you have questions, feel free to add them into the chat or raise your hand and we'll call on you. But in general, we'll sort of run for 40, 45 minutes in the talk and then take most of the questions at the end, unless there's sort of clarifying questions. Thank you very much for joining us, Dr. Parker.
Great. Well, thank you very much for the invitation. It's an honor to be here. And thank you, particularly Esther, for your coordination of my trip. I appreciate it very much. So I'm going to talk today about statistical practice and research at NASA. The pictures at the bottom are kind of a collage of work that I've done that ranges everything from Mars to soybean crop production in the Midwest. And I'll talk about some of those as I go through. And I'll focus both on the statistical research opportunities, where I want to leave sort of this discussion that we have, the type of problems that we work with. So, first of all, I want to tell you where I'm from. I'm from NASA Langley Research Center, which is one of 10 NASA centers in southeastern Virginia. It's about a 3-hour drive south of Washington, D.C., if you're familiar with that. And Langley has a very long history in aeronautics. It was established in 1917 as the first civilian aeronautics research laboratory in the United States. And so we celebrated our 100th birthday anniversary in 2017. This?
Yeah. Sorry.
Oh, she's gonna do it.
Thanks.
No problem. I couldn't see it. Thanks for telling me. I missed the words on that side of the screen. Okay, great. So 1917, I will tell you that Orville Wright was part of the founding of what was then called the National Advisory Committee on Aeronautics, NACA, N-A-C-A. And when NASA was formed in 1958, Langley Research Center became one of the first NASA centers. So we predate NASA in that sense. We have buildings still in our center that have NACA stone on the facility. It's also the home of the first astronauts, the Mercury 7. So if you've seen Hidden Figures, that movie about the human computers, that photograph where they meet the astronauts was taken in front of this hangar right here, and that is right behind my office. The original Space Task Force was centered in Hampton, Virginia. That's where I'm located. And a little bit farther in the distance, you can't quite see it, back here in the back, which is about a mile or two from my center, is my office, is where Neil Armstrong practiced landing on the moon. It's a facility that created 1/6 of gravity. And when he did the lunar lander, he practiced at that facility as well as the other astronauts. There's a famous quote from Neil Armstrong that when he asked what did it feel like to land on the moon, he said, "Just like at Langley." So now we work in, NASA has sort of 3 big areas: space exploration, so that's both human and robotic; aeronautics, which includes both aircraft and air transportation systems, like expansion of the national airspace; and then Earth and planetary sciences. So viewing both our Earth, but also other planets. And I know that Amy Braverman spoke into this series last week. She works predominantly in that Earth and planetary science area. So Langley has a very long history, and that's an important part of my story as we go through today. All right. So do we have to click back on once it was clicked over? Maybe. Okay, how about that? There we go. All right, I'm back now. This is an overview of my presentation. I'm going to give a little bit of background, a little bit of history. As you can tell, I like sort of aerospace history. You'll get little bits and pieces, and if you want more, I can bore you to tears. More NASA history. But I'm also going to talk about how did I get in statistics. You've heard my multidisciplinary background. I'm going to focus on practice. And in practice at NASA, it's very important that practice involves collaboration and influence. I'm going to focus on those two topics. And then I'm going to give you a collection of case studies. This is not going to be a deep statistical talk on any of those. I give references in the slides if you want to read more, or if you want to ask me more about methodology. This is more about practice and research opportunities, my talk. So there's sort of a plan for what you should expect to see. And I'll focus on some specific statistical contributions that came out of NASA work and research opportunities. So here we go. So as my introduction, Ron said, NASA has created some of the most unique, complex, awe-inspiring systems in history. And infusing statistical practice, statistical engineering, which I'll talk a little bit about that word, over the past 25 years has now gained much broader acceptance in applications. It's become more commonplace. And that required technical and organizational impact. And those methods now are ubiquitous in aerospace research and development. So there's been a process. And I say that because there isn't a statistics sort of history like I would like to be able to claim about NASA. A lot of people practicing statistics, but not as a well-known group as you would have at other government agencies. The example is at the National Institute of Standards Technology in the United States. They have the Statistical Engineering Division, which was founded in the 40s. We don't have quite that story at NASA, but we have influence, and I'm going to point that out. And my last point is that in the practice of statistics at NASA, oftentimes I'm called for mission operational decisions. A rocket is on the pad. We need to decide whether we've got managed adequate risk to launch or not. I don't have time to evaluate and compare lots of different statistical approaches. I have to come up with something. I have to manage the risk of what that is. I have to explain it. But we are very much interested in then using those near-term decisions to motivate statistical research such that we're better prepared for the next time. So there's this mix of immediate solutions, often insufficient time, but then that motivates a lot of our statistical research, which is then done after that mission takes place. So here's a quick overview. My personal background in statistics is industrial statistics, particularly my PhD was in response surface methodology, an area of design of experiments. So you're going to get a little statistical design of experiments, parallel timeline with aerospace. I have a whole talk on this, but you're going to get it in one slide. So on the upper left, the Wright brothers flyer, first heavier than air flight, 1903. The lower left is the variable density tunnel. This is on display at NASA Langley in 1921. It was the second wind tunnel at NASA Langley. And people ask, so did the Wright brothers use statistics? Did they use design of experiments? Well, Ronald Fisher and a lot of his work that we talk about and focus back on is contemporary to that. It's in the 1920s. It's actually after the Wright brothers flew. And I like to quote a colleague of mine, Doug Montgomery, who says that the Wright brothers used Edisonian techniques. And if you know about Edison, he said he tried 1,000 things, right, to find the filament of the electric light bulb, but the challenge was going on to 1001. Early aeronautics, they just tried a lot of stuff. And they were very successful, but design of experiments and statistics and that way we think of it now was not infused at that time. And I don't think that's a criticism, it's just an awareness of it. So then I mentioned that NASA was formed in 1958, part of the space race. And the Saturn V rocket there is in the center. And so contemporary to that is the papers by George Box in 1951 on the attainment of optimum experimental conditions, which is sort of the initiation of response surface methodology. It's taking design of experiments from an agricultural setting to more an engineering, immediate response type setting. And so that's happening sort of contemporary. I will tell you that the development of the Saturn V rocket came out of the Army Missile Ballistic Command, Warner von Braun, and the Army took a very early interest in training on design of experiments. There's some great interesting conferences that were set up in the 50s at that time. And so I do believe there was influence there at the time, contemporary-wise. 1969, Neil Armstrong walks on the moon. And in 1966, there was a paper I'm referencing here from the American statistician called Some Statistical Applications in the Apollo Program. And the quote in the box says that most of the statistical work is performed by engineers and scientists, some well-trained in statistics, others having only a passing acquaintance with the subject. That was written in 1966. That quote is still relevant today in the world that I live in. I work mostly with aerospace engineers, mechanical engineers, electrical engineers, some physicists. They've had some training in statistics. I'm going to tell you a little bit about my own personal story, but most of it is a passing acquaintance with the subject. And so it's really fascinating when you look back, that's some 50 plus years ago, right? The space shuttle was first one in 1981. First flight was actually in 1980, I believe. And that's the same time as sort of the quality movement in the United States and in North America. Deming, Taguchi, those were all in the 1980s. So there's this parallel timeline. And I think the point of that story is that statistics has been infused in different places. But when I came working with NASA in 1989, first in private industry, I had never been exposed to anything like design of experiments. I had never been exposed in my training or experience, and that's true of most of my contemporaries. So how did I get here? Well, I call it an engineer's statistical awakening. Traditionally, engineers are trained with a lack of relevant, applicable, practical courses in statistics. This is in my time frame in the 80s. I think there's been great improvements of that at the time, but this is my story. So in the 80s, when I was an undergraduate engineer, I took one statistics course, and it was awful. And it was the professor's fault. They taught a watered down math stat course, card games, dice, colored marbles out of an urn. And I thought, how am I ever going to use that in my engineering profession? There was nothing applied. If you had told me that within 10 years I'd be in a graduate program in statistics, there's absolutely no way that would compute, right? But that was my introduction. And I would say generally engineers like myself are trained to fear uncertainty. An engineer once said, replication causes error. Let's think about that for a minute. If I run the experiment once, there's no error. Is there no error? Really? I run it twice and I get an error. And so what do? That's 2 out of 3. That's what the engineer said. Got to run it at least 3 times. Famous engineer said that to me one time. Never run an experiment twice. Always 3 times, because then you pick the best 2 out of the 3. And you're chuckling, but this is sort of the environment that I came to be in. So in 1999, I stumbled on a 20-year-old paper written by a visiting statistics professor to NASA. And that professor wrote this paper about calibrating a device for a wind tunnel test that was radical. And we thought he was just crazy, actually. I mean, I wasn't around at that time. I came in '89, but it was just kind of pushed to the side, that paper. He proposed more than an order of magnitude reduction in cost and effort to calibrate a device that took 3 weeks for one person to calibrate. And it was just mysterious. We looked at the paper, myself and 2 other PhDs who had had no exposure to it. We thought he had invented something. What he put down was a spherical central composite design applied to our application, but we had never seen one. And so these radical concepts of statistics were exposed to me about experiment design starts with questions, not data. So most of my world at the time was you get the data, then you think about what you're going to do with it. Not targeting how we get the data, but targeting what data are required or what to collect. Factorial experiments, to an engineer, that's chaos. Changing more than one factor at a time, that's absolute craziness. You know, we hold everything constant. We've changed one at a time. That's the way all the labs were done in our engineering courses. Change more than one at a time, extremely efficient, but it seems chaotic if you don't understand the structure of it. And modeling involves a lot more than just plotting the data. In my day, that would have been plotting the data and overlaying the transparencies. It involves things like estimation and testing of significance. Those were all radical concepts in this one paper. And so what did it lead to? It led me to go back to graduate school, and that's my story. As I found that to apply these broadly, I needed to know more about what was under the hood, not just be able to use textbook solutions. Funny story, I advocated to go on graduate leave from NASA, stood in front of my leadership, and I said, I want to go back and get a PhD in statistics. And they said, you don't have a statistician, do you? And I said, right, maybe this is the opportunity for one. It's a funny story in retrospect, but that was true. Most people went back for graduate degrees in aerospace. So I discovered these new powerful techniques to learn and gain deeper insights. So I go off, I come back from graduate school, and my very first project, real project, freshly minted PhD, is the world's most powerful solid rocket motor. How's that for a final exam, right? The idea was that NASA was going to adapt one of the reusable solid rocket motors off the space shuttle program into a different configuration to use it as a single stick, like this. Leveraging space hardware is extremely advantageous for reliability, data, all those things that we know. But what was different in that single stick configuration is we had to know what the propensity was for it to spiral, like a rifling motion when it took off. That was never important in the shuttle where there was two, and the main engine had sufficient control authority to not create a spiraling action. And so we did full-scale motor firing. That is that rocket, 12 feet in diameter, 120 feet long, laid on its side, bolted to the ground at one unique test facility in Utah, and fired full-scale, 2 minutes. The flame deflector on the motor is the side of a mountain. There's a gouge on the side of the mountain. And every one of these tests is very expensive. I say that because when I got involved, they had already done it twice. And it takes about a year to plan for each one of those tests, 6 months to a year, and they hadn't got the answers they wanted. And I had, as I told you, back to my stumbling into the force measurement paper, had force measurement experience, and that's what got me on this project. It wasn't because I was a statistician that knew design of experiments. It's because I had this subject matter expertise. We worked the project, we characterized the motor, and in 2012, there was a full-scale launch of what was then called Ares 1X. Now, this configuration has gone away, but if you watched the launch about a year ago, the Space Launch System, NASA's new space architecture, you'll see two solid rocket motors still on the side. They've been extended a little bit, but they're the same basic solid rocket motors this contributed to. Now, this was a big opportunity to highlight design experiments, and it was a big deal for NASA to recognize. In fact, we got a group award from the NASA administrator, and I was selected to accept that award. And I don't say that to brag, but I say that I just told you about 5 years earlier, somebody said, we don't have a statistician. Do we need one? When I went back to graduate school. So this was my first sort of project after grad school. Now, I work with lots of discipline areas, and in NASA, having a statistician on the team is not a requirement. It's not like in pharmaceutical industry where you have clinical trials and a statistician is required. At NASA, a statistician has to be invited to be part of that team. And that requires a track record of how well you can collaborate. I've talked to some students earlier today, and I was talking earlier with Rowan that when people come to NASA, they may have this very impressive academic CV and training. But to me, that's only their ticket to be sitting there in the interview. It's how well can you work with other people? How well can you interface with other disciplines? How can you ask questions and learn what you don't know? That's absolutely required at NASA. And so I want to say that sort of in an inspiring way. I've been honored to give some guest lectures by Nathaniel Stevens at University of Waterloo. I do them virtually and in his consulting course. And I focus on this topic about collaboration. And I distinguish it between consulting and cooperation. I've got a chart that comes up next, but that sort of fleshes that out some more. But the main idea is that collaboration is when you're a full team member. You are not a support function. You are at the table where decisions are made, choices are made about decision-making of the next set of experiments to run or the decisions that are going to be reported out. You're not off just analyzing the data somewhere in your cubicle. I had a leader one time that said, Pete, if you're working on projects that you can solve at your desk, you're not working on the hardest projects that I want you to work on. The hardest projects always involve multidisciplinary collaboration. And what that leads to is a topic that I've had a lot of energy around recently is statistical influence. How we influence our organization, both individuals, the organization to embrace statistics, and between organizations. And I use the definition here from the American Dictionary of the English Language. I always think that's funny. You know, we Americans don't speak English, right? Two countries divided by a common language, I've heard it said. That is a power whose operation is invisible and known only by its effects. So demonstrated benefit. And that's why I told you that story before about the award from the NASA administrator too. People didn't really understand what the value was of a statistician, but they understand the demonstrated benefits. And that's what influence is, and it changes the culture. I'm not going to belabor this slide. I'm going to make my slides available, but I had a very interesting experience with a year and a half with a PhD student who was in industrial organizational psychology. And he had a strong statistics background, but he focused on collaboration, particularly of geographically diverse teams. And I would take him around the meetings at NASA, and he would tell me sort of the science and the research and what was happening in these meeting dynamics. It was fascinating. We did a talk together called The Art and the Science of Collaboration. The art was my experience. The science was his research. And this is a way to kind of give yourself a self-test. Are you a consultant or are you a collaborator? Who's doing most of the talking? Consultants is mostly monologue, directly giving advice. Collaborators is dialogue, back and forth. Do you speak in statistical terms or application terms? And I'll tell you the simplest test for team members of mine when they come back, how I figure out where they are in the team is if they come back to me whining that the team is not accepting their approaches. Well, they just defined to me that they're not a collaborator on that team because it's the team, not my team. So I would really encourage you to think about that. That's some of the biggest impact we have had is seeking to be collaborators. And there's a great paper by Bill Hunter in 1981 called The Practice of Statistics. The real world is an idea whose time has come. And he has this simple diagram of a subject matter expert's role and a statistician's role on the bottom. And this is really a self-perception of what you think your role is. And I'll kind of walk through this chart. In the upper left, the statistician and the helper is typically the consultant. The subject matter expert is active. The statistician goes off and does the analysis or the planning and brings the answers back. They're a helper. The bottom right corner I refer to as the overzealous PhD, freshly minted graduate who feels their job is to enforce statistical purity, I'll call it. And sometimes the subject matter experts will just step back and become passive. That's not really a good place to be because when it doesn't work, it will be the statistician's fault. The upper right corner is a collaborator where you have both active, you have both engaged, mutual respect of both roles, seen as equals in disciplines, so whatever it is. And I argue that is required for effective collaboration. One of the most rewarding things for me is to see a subject matter expert present the statistical results from an analysis. They own it, they embrace it, they understand it well enough to stand up and present it and take questions. That's the biggest sign of success for me of collaboration. And I will tell you that collaborators start with asking questions and don't just assume that they've been given the right problem. And in fact, some of the biggest contributions that I've made over the years is helping to define the right problem. There's a paper by Kimball that I've sort of borrowed the title for called Errors of a Kind. You know, we talk about type 1 errors and type 2 errors. A type 3 error is a very sophisticated solution to the wrong problem. And John Tukey says it's better to have an approximate answer to the right question than to have a precise answer to the wrong question. These are very insightful quotes about many times when collaborators or multidisciplinary teams think they know the right problem and they're just looking for statistical tools or analysis to apply to it. Always best to ask questions. And sometimes that's my biggest contribution and I go away actually for projects, is just helping define the right problem. And one way to do that is a series of questions. If you Google these, you'll see things called like the Hellmeyer Catechism, George Hellmeyer, names down here. He said he developed these set of questions to manage the resource demands of how much it's going to cost with the demands of the researchers or the scientists, how much they want to learn. So he would ask these questions. And the very first question he would ask is, what are your precise objectives? In my experience, sometimes I have a subject matter expert come in my room. Sometimes they've been sent to my office, which is not always a good start. And I say, well, what is it you're trying to achieve? And they say, well, I need to build hardware. Then I need to get into this facility for so many weeks. And I need to collect this data. And I say, no, that's not what you need to do. What you need to do is learn. You need to answer questions. We never subject ourselves to the cost of experimentation unless we think we're going to confirm something we already know or discover something new. It's expensive to collect data, whether that's gathering data or whether that's conducting an experiment. And so I sort of press that back. Yes, we may need data, but first thing we have to do is define the right questions. And they'll say, well, I want to know if system A is better than system B. And I look at them and I say, well, how will you know when you're done? How will you know when system A is better than system B? Well, this requires them to think about performance metrics, criteria, what makes it. So these are all statistical questions in disguise. I'm talking about defining factors, responses, the comparison between them, what kind of methods might be used. And then I ask, well, who cares if we solve the problem? Because those are the people we have to communicate to the impact of the success of that project. And from this, it's kind of a disciplined approach. Instead of I say, well, what are your factors? You know, I might get just a blank look. I get them to explain to me in their terminology what are factors, responses, and what's important, and who cares. And then we ask the question for project managers, well, how well do you need to know the answers? So I've worked on everything from human space flight to very early research and development, concept development. You know, nobody wants to be wrong, but being wrong with early concept development has a much different impact than being wrong with human space flight. And so that scales. That scales the size of our experiment, how much risk, what are the consequences if we're wrong? This gets to sort of the cost of the experiment and that it should match based on a very defined set of criteria. So everything I've just described is in a discipline that you may or may not be heard of, statistical engineering. And I feel sort of incumbent to have one slide in here. It's not meant to be a plug for an organization, but there is an organization called the International Statistical Engineering Association. Myself, I served as chair of it at University of Waterloo. Stephen Steiner was the first chair of that organization, if you know him. And Nathaniel Stevens was also chair of that organization. And it is a systematic integration of statistical concepts, methods with other disciplines. That's everything I've just described, the practice of statistical engineering. It is not just the words flipped. It's not engineering and professionals, and it's focused on this idea of sustainable results. So changing organizational culture. If we solve one problem and it's a big impact, that's great. But if we solve that one problem over and over and over again, then there's more impact to the organization. So I would encourage you to check that out. The website is I See a Change. You get this catchiness. That's a sketch. For marketing, iseeachange.org. So now I'm going to fly through a couple of some case studies just to give you a flavor of the type of work that I've done. This is going to be a little bit like speed dating, but if you want more information, I'm happy to provide it. So on the left involved using NASA satellite data, particularly one that measured tropospheric ozone residual, to provide information to soybean farmers in the Midwest. Soybeans are susceptible to ozone events. It damages their production. And if a soybean farmer knows that an increased ozone event is coming from the West Coast to the East Coast, they can take mitigating strategies, one of which is they can over-irrigate, which causes the plant to close. And it's been shown in laboratory studies that that minimizes the effect on the plant and its yield. So can we use a NASA data product that was originally put up to research the atmosphere for a practical application? That was this project. And we had data over 5 years, over a collection of counties of 3 states in the United States. And we developed a very simple statistical model. If you look at the paper, a very simple statistical model that involved a correlation with 3 factors, multiple linear regression. The researchers had never seen anything other than correlation factors between 2 factors. The concept that you could correct for yield as a function of temperature, moisture, this was just not in their experience base. So you'll look at that paper maybe and say, that's really simple statistics. It is, but it was a really big cultural change for that group. The one on the right involves making a case for a launch that was about to be delayed. So NASA monitors the atmosphere and we need to have overlapping missions. We don't really have a way to calibrate most of our sensors in space. And so the way we do it is we have these overlapping missions. And imagine 2 missions are launched, one instrument and a second instrument. And if they overlap, then we can tie that record together because it's about the trend. It's not about an absolute value. And if we have a gap in a launch, it would look sort of like this. And these are seasonal variations that you see the up and down. It's not random variation. We used a very simple approach to make a case to not have a gap in the launch. A very practical application such that that gap could be interpreted as an increased trend. This is a simple plot. It tells a really powerful story that the mission manager in these flights and not have overlapping is very convincing. Simple is always good. Aerospace wind tunnel testing. So as I told you, Langley's aeronautic history. This is a test of what's called a blended wing body. And all of these individual control surfaces along the back edges can be moved independently. And if you want to characterize that and you want to do it 1 factor at a time, it's just not tenable to experiment that way. So this paper explored a very high dimensional response surface method with lots of factors to improve the efficiency of testing. And on the right is helicopter testing for the US Army. This is a small helicopter that's tested in a wind tunnel and the propeller is running. It's mounted on this post. And a pilot is in the control room who actually responds to the inputs from the wind tunnel. It's a very expensive test. Cost per hour is the most expensive of a powered test. And we used design experiments to show how that could be done more efficiently. And also it was another one of these ones of a sort of cultural change. So you're getting my flavor in design experiments, right? That's my background and I'm the speaker. So I told you about the paper I found 20 years that started me to statistics. This is the project on the left. It led to patented systems that saved $500,000 a year and still do. It changed calibration time by an order of magnitude from 3 weeks to 3 days, nearly an order of magnitude. You can look that up if you want to see more about it. And the one on the right was a way to put atmospheric measurements in the hands of school students, middle school students all over the world, to engage them in atmospheric sciences. And we can't send them a very expensive spectrometer. And this was to measure ozone. So they came up with this technique of making a simplified instrument. And how can we make it good enough, right? This is the decision about not perfect, but good enough to send out to schools to make it inexpensive. And that's what this project is. This device is called a Zircua. You see it written right there, which means something like, it was an African language that meant measuring what we can't see. That was the name of the device. Okay, so now I want to kind of round out my talk here. I think I'm in good shape for time. On areas of statistical research, at the top, I have areas that we've done a lot of work in, and I feel like we've had significant contributions, and these are not my contributions, by the way. These are contributions that work that I've been involved in with NASA has had. Restricted randomization, so that's split plot designs, and second order response surface designs. That was my PhD dissertation area. It's a famous statement that if you take a design of experiments course, you'll see randomization, right? Randomization, randomization, randomization. When engineers take that, they flip a switch and say, I can't randomize, so I can't use anything related to design of experiments. There's a famous quote by Cuthbert Daniels who said, every experiment has hard to change factors. To change a factor in an experiment is hard by definition, instead of doing nothing. And so this notion of what's hard to change, very hard to change, what's restricted on randomization is a very practical approach. And that is an area that I worked in. Space filling design. So these are Latin hypercube type designs in nested structures. This was used on national aerospace applications to increase the density of planes coming in and out of airports, something I would have liked to have had last night when my flight got delayed in New York, where they had to throttle back and restrict the flights going into LaGuardia. And I sat on a runway in Virginia for an hour and a half. But that was this project. And David Edwards at Virginia Commonwealth University had a collection of students that worked on that area. Dose response modeling for psychoacoustic responses. I'm going to talk a little bit more about this on another slide, but this is work that was done by Allison Wilson and one of her students at NC State. And it involved noise, community noise, annoyance. The noise is the dose. So think about clinical trial, but the dose is noise. And whether people are annoyed is the response. Highly annoyed. And I'll talk a little bit more about that. Reliability experiments and design and modeling. For very costly experiments, my graduate professor advisor, Jeff Vining at Virginia Tech, as well as a collection of students involving Laura Freeman and Ann Driscoll and Jennifer Kinsler, all worked on this for a number of years and published quite a bit in it. I'm going to highlight a couple of current statistical research areas that maybe will motivate you to think about problems and solutions. One of them, the general theme of both of them is small sample sizes to characterize rare events. And you should read that and go, you shouldn't do that. I presented this at JSM in Toronto here this past summer, and somebody in the back of the room said, you're doing things that shouldn't be done. So I get that, right? This is not what we choose, but that's what we're afforded. That's what we have, and we still have to make a decision. And I say, well, what's the alternative? A gut response? Or do we use the best methods we can? And particularly ones that involve binary or ordinal categorical variables. And for NASA, statistical methods, you've probably got this theme. If you look at the papers, the techniques have to be approachable and intuitive to engineers for them to trust and to be adopted. Okay. So let's talk a little bit about dose response modeling with limited dose range of rare events. And I have two examples here. One involves non-destructive evaluation. This is where we use imaging techniques or non-invasive techniques, much like it's used in the medical industry, computed tomography, an MRI, ultrasound, but we do it on metallic objects that are fracture critical. That means if they fail, disaster happens on human spaceflight systems. And the way it's done is we present an inspector with a collection of flawed and unflawed specimens. That inspector reports back whether they found the flaw or they didn't. Obviously, we put false positives in this with no flaws. And from that, we want to model the response, which is the probability of detection as a function of the flaw size, but over a very limited range. I'm going to show a plot of that. Maybe only from 70% to 90% probability of detection because making these samples are expensive. And we want to report that with statistical confidence. Second example I have is on community noise. I mentioned you may have seen in the news last week, the X-59, NASA's new experimental aircraft was rolled out. The paint job was displayed. It's a classic NASA thing to do. That's a picture of it, a graphic artist rendition, and it is to do commercial supersonic transport research. Right now, commercial planes can't fly supersonic over populated areas because it's sonic boom, because it's annoying. The Concorde, when it flew, could only go supersonic over the ocean. The idea here is to develop an aircraft with a very long skinny nose, we can see right now in the picture, to tailor the sonic boom into what's known as a sonic thump. Something much more attenuated that would be tolerable. And the way we're going to test that is we're going to fly over actual populations in the United States and collect community annoyance. And at some point, the regulators are going to decide that some percentage of people, it's acceptable to be highly annoyed. Not just annoyed, highly annoyed. So probability of annoyance, the dose is the intensity of the sound. So here's a plot where I'm going to just kind of briefly go through this, but I've got some dots here about zeros and ones, binary response, non-destructive evaluation. And the first thing you look at and you go, well, there's not many of those. That's right. About 40, 60 data points. They're not very well distributed. So you don't see like large separation and overlap. And yet we're going to fit a logistic curve to it. And we want to predict 90% probability of detection. And we want to predict it, imagine a confidence interval on this side, 95% confidence. So it's a tolerance interval. I'm going to talk a little bit more about tolerance intervals in a minute too. And so you look at that, and the first question is, I told you that's a logistic regression model. We really are interested in guidance on when that traditionally modeled strategy is not supported. So if you do a dose response relationships and you take like a bioassay course like I did when I was a grad student, you see everything from no response, 0% to 100%. You see this distributed plot. You fit this full curve, or a lot of clinical trials are that way as well. We're only focused in one region. On this example, we're focused in the upper region. On the annoyance example, we're focused on the lower region. And I'm going to argue or just sort of say plainly, I don't think fitting a logistic regression model here is really appropriate, but that's what we do. And what is the guidance about doing that? And then considering other alternative approaches. Okay, that was quick. I hope you get it. If you don't, I'll answer questions about it. Two more examples. This is about tolerance intervals. Very expensive full-scale tests, very few of them, and yet we still need to say something about the likelihood of an extreme performance event happening. This is parachute drop testing. Parachutes are some of the most complicated aerodynamic decelerators that I have seen. There's a lot of art to the way they work, and they basically are qualified by a full-scale flight test like this. They have a test bed they push out of a helicopter or higher and test those parachutes open. That's what it looks like when you see a spaceship coming back, human spacecraft. So very small sample size with extreme conditions, and we want to know about engineering conservatism. And on the right is a similar one. This is an inflatable heat shield. Right now, we're limited to landing on Mars by the size of the rocket or the size of the heat shield that we can put in that rocket. If we make an inflatable heat shield like this, comes out, then we can land a larger science payload on the surface. So this was research on that, but once again, that's a complex structure. It goes through full-scale testing, and we're interested in very low probabilities of failure. Most of what I do is in the very low tail probabilities, not 1%, 1 e⁻⁶, and that's kind of the beginning. I look at 1 e⁻⁹, 1 in a billion cases. So here's an example. This is the one that I got. Hopefully that person from JSM is not online or here. When I showed it, I have 14 test values and I'm going to do distributional modeling. You say you shouldn't do that. What else are we going to do? And I show here two examples of, this is a Weibull distribution and smallest extreme value. They're just related by a log transformation. And I show this on a probability plot. You see the 14 dots, a 95% confidence region around each. The green is Weibull, purple is smallest extreme value. A 90% probability there, which is known as a basis, a statistical basis of strength, which means we expect 90% of the population to exceed that value, is shown by this line, and then a 99% basis. We expect 99% of the population to exceed that minimum strength that we're going to design to. You look at that plot and you can see the difference based on what distribution I pick. So which distribution should I pick? Well, there aren't really tools to do that. We think about it, I look at that graphically, I think about conservatism, I look at focusing on the lower tail, I look at the trajectory of the lower tail, which almost looks like it goes toward a threshold distribution. If you notice that concavity at the lower tail. But I would like to see some methods that do goodness of fit tests over a portion of a distribution, right? It's a fit test, they're over the entire distribution. I don't really care about central tendency and I don't care about the upper end tail. I just care about the lower tail. And so those are an open area of research that I've done some work on non-parametric or pseudo-parametric techniques. You're familiar with any of those where we just look at the last few points of the distribution and we don't make a distributional assumption. These are parametric distributional assumptions. There's lots of ways you could attack this. And we have a paper coming out in quality engineering and reliability engineering on that. So some concluding remarks. I think I'm right on time. Is that good? Okay, good. NASA has this rich heritage of all these awe-inspiring things, and I stand, on this incredible shadow of all this work. It's quite a humbling thing to do. And statistical collaboration now, I'm so happy to see that it has become so much more ubiquitous and common in engineering at NASA. But we still have challenging NASA applications, and those naturally define statistical research opportunities. And the last box in yellow is kind of my thought in that I personally believe that advances in statistical methodologies will help us better achieve our missions. And with that, I'm happy to stop and take any questions.
Are there any questions in the room?
Yeah.
So in terms of encouraging this collaboration, what have you found, or maybe there isn't one, and is sort of like the biggest challenges for, especially in the engineering environment? Is it really just that pure statistics that you have to overcome, or is it other attitudes or dynamics between engineers and statisticians? Like, great experience.
Yeah, that's a great question. And I think that it has a lot to do with the specific engineer's experience, whether they have got, like me, one help them to work together to adopt their problem to solve. not just throw a solution at their problem, which would be more of a consulting position. And, you know, there may be some nuances here in the way that I define consulting and collaboration, but the idea is that I care about the solution. I care about your solution as an engineer. It's going to be a lot more inviting. So what am I going to do? I'm going to ask you a lot of questions, engineering questions, dumb quote questions. And that develops a relationship that allows them to ask you, quote, dumb statistical questions. That's the best advice I can sort of say. And expect that in some cases, it's just not going to be really welcomed. I mean, in my case, I experienced a lot of that early on 20 years ago. I don't experience that as much now. I think there's a lot better engineering undergraduate education and statistics. A lot better textbooks that were available then. It's more applied in nature. So I think generally they come out a lot more prepared to be acceptable, but they don't have all the tools, you know. And so it's really about mutual respect. I mean, all the things I'm saying are in the literature of multidisciplinary collaboration, whether it's a statistician or whether it's two other disciplines. These are all basic sort of developing innovative collaborative research involves these common sort of threads: respect, trust. Yeah.
Looks like you have a small end issue, but I still want to ask the question whether how often machine learning, particularly in city was I mentioned.
Yeah, so I didn't mention it's not an area. It's not an area I work in. There is a lot of work in that area. Now I am a small data guy. I mean, that's the type of problems that I tend to get all the time. There is some projects that I'm working on right now, which are looking at historical databases, taking advantage of a lot of historical information that I expect to do that. But, you know, as a whole, I don't know, and this is going to go in the recording, I don't know of a golden example at NASA, one that you can hold up, where, you know, machine learning has been demonstrated yet. And I don't think that's a comment on the technique. I think that's a comment on the application. I think it's been used in a lot of areas it probably shouldn't have been used, because the tool within NASA has gotten this buzzword. So I think it's just time. I think it's where we are right now, but it's not my specialty, so I don't talk about it. I don't know if Amy talked about it last week, Amy Braverman from NASA, she talked about it. I expect she has much larger data sets at NASA, and certainly people in more of the biostat work, you know, at human spaceflight centers. So you got my slice of NASA. I'm not here to say it's the whole thing.
So I understand that the experiments are very expensive, so but I really want, I think I really see people approach the problem by asking questions rather than collecting the data.
Yeah.
But I still wonder whether the data, there's no culture of collecting data. I mean, even from my experiment, I don't
So typically, the way experiments were designed before, and maybe some still now, is people decide how much money they have and how many data points they can select. And when they run out of money, they're done. It's a very bad way to do it. And I sort of confronted people with that. And they go, well, that's all the money I have. And I said, well, then you should go back and either rescope your questions, say what you're going to answer, be more narrow, or go advocate for resources. One of the benefits of design experiments is that you don't have enough data. It is definitely a cultural aspect of engineers, you know, that they don't focus as much on that front end discipline of defining the problem, factors, responses, what data do I need? It's just go get it and then I'll figure it out. And I speak, I mean, I don't say that in a negative way of engineering. That's where I was. I mean, that was my perspective as well. You know, I told you the story about the system that changed in order of magnitude reduction. Let me give you a little more details on that. It's 3 weeks of calibration, over 700 data points to estimate second order model in 6 factors, 28 coefficients, over 700 data points. And we look at that and we go, probably in this room, we're going, that's crazy. Right? That's way too much data necessary for a very high precision, by the way, calibration experiments, not noisy data. At the time, others in the world were saying that wasn't enough. Our German colleagues were proposing twice that, 1,400 points to estimate 28 coefficients. The method that I showed you that kind of got me interested, under 100 points, 60-ish points. Think about a spherical central positive. To go from an order of magnitude like that sounded just unbelievable because the focus was on the quality of the information, was on the amount of data that was collected. You know, a million points is good, and 1,000,001's a little bit better, but not much, right? And this was just kind of the mindset of it's about N, not about the information content of the data that we collect. And I think that's one of the distinctive differences about a statistical approach, at least from an experimental point of view. Observational point of view, I mean, you want all the data, right? Historical data you can get, but from experimental, where you have to pay for every one of those data points. And you still have to pay, I would say, for observational data, you collect it, retrieve it, scrub it. But does that help? Answer? Yeah. Yeah.
Are there any questions online? So we've just got 2 minutes. So just briefly, do you have any advice for PhD students interested in sort of not getting into NASA, but you know, getting into NASA?
Yeah, getting to NASA.
Broadly speaking.
Yeah, I mean, I think regardless, you know, you've heard me focus on collaboration, regardless of where you go. Collaboration is, I think, an underappreciated aspect of your training, and it's just really hard to do, I think, in an academic setting. I mean, I'm just admitting that, right? So internships, being involved, you know, getting involved, don't just think you want to work in some industry or some government agency, but focus on being more than just a consultant. That's my sort of encouragement to you, because that will provide much larger impact for you personally, professionally, and for the organization. You know, in terms of aerospace, things are all changing now with so much more commercial aerospace. We have commercial partners flying much more than NASA is flying. SpaceX, for example, Blue Origin, Boeing. And so the idea of aerospace is changing. It's becoming a bit more toward the direction of what the airline industry went through at one point. Deep space, obviously, it's a bigger deal, human spaceflight to Mars, but I think there's a lot of opportunities in aerospace that or it's just a changing culture where it was very few sort of launches. I mean, SpaceX last year, I think, launched over 100 launches or something in that range. That's the space shuttle launched somewhere around 100 its whole career. So in 1 year. So there's a big difference in the amount of access to space. And so that's one area I think there's a lot of opportunities in.
Thank you.
Yep.
So next week we have for folks in person, it will be Zoom only because Sarah will be remote. It's Sarah Algeri from Minnesota, but that will be Zoom only. And then the following week we will be back in person here. Thanks very much for everyone who joined us on Zoom. I'm not sure if the cameras there. Thanks very much for coming on Zoom. Thanks very much for coming in person, and thank you very much.
You're welcome.
For joining us.